I have discussed the solution of this problem in part 3 of my math video lessons. In that discussion, I summarized the increasing and decreasing patterns between the members of this sequence that turned out to be the key to the solution of this problem. If we agree to call odd positioned members odds and even position members evens, then these patterns can be described as follows. Every even is greater than the odd that follows it. All odds are increasing. All evens are decreasing. From that it follows that all odds are less than all evens, since the smallest even, number 2010, is greater than the greatest odd, number 2011, that follows it. These patterns are illustrated in this diagram. I left it to the viewers to prove that these rules are correct. Well, now we can prove them as a separate exercise. The method of defining the values of members of this sequence is called recursive definition, in which the formula for each member of the sequence uses the previous member as its argument. In any high-level programming language, it's allowed to enter recursive formulas in a computer program, and the computer automatically computes all the members of the sequence. Of course, a programmer must specify the criterion of when to stop, otherwise the program will crash. Usually, such criterion is a number of iterations. In our case, it's 2011. Since the formulas in a recursive definition are the same for each group of consecutive members of the sequence, we can be certain that any pattern established for the first several members in the sequence is consistent throughout the entire sequence. Okay, let's write down the formulas for the first 6 members of this sequence the way they're defined in this problem. To prove that our rules are correct, let us first formulate the general rule for all members of this sequence. Since they all are some powers of decimal numbers in the form 0.201 and some more decimal digits, we can be sure that they all are positive real numbers that are less than 1. Let us look at the graph of an exponential function in which the base is a positive number that is less than 1. In this example, it's the graph of function y equals 1/16 power x. We see that the value of y starts at 1 for x equals 0 and decreases as x increases. For x equals 1/4, y equals 1/2. For x equals 1/2, y equals 1/4. For x equals 1, y equals 1/16. Let's use this rule to evaluate what happens with the members of our sequence. Notice that the first transition from odd to even, that is from A1 to A2, the base increases and the exponent decreases, since A1 is less than 1. We talked about it earlier. So A2 is greater than A1. Let's use this fact for the next transition from A2 to A3. While the base in this transition decreases, the exponent increases. So A3 is less than A2. And so forth in chain. A4 is greater than A3, A5 is less than A4, A6 is greater than A5, etc. Every odd is less than the following even, and every even is greater than the following odd. That proves our first rule. Let's now compare A1 and A3. We see that the base in A3 is greater than in A1, while the exponent A2 is less than 1. So A3 is greater than A1. Let us use this fact for comparison between A2 and A4. We see that the base in A4 is less than in A2, while the exponent A3 is greater than exponent A1. So A4 is less than A2. This pattern is sustained in all the following members. This proves our remaining rules that all odds increase and all evens decrease in this sequence.